Hello students, welcome to the series of lectures on digital speech processing. So in this video I'm going to explain about the time domain methods for the speech processing, that is short time energy, and this is one of the most important time domain method, how we are going to be analyzing the speech on a continuous basis. So let's get started. So on completion of this lecture, you'll be able to illustrate how a digital method that can be applied to speech with the help of the short time energy. So this is the time domain method actually, which involves the waveform of the speech signal directly, that we already know about this. And when it comes to the frequency domain method, which involving some form of the spectrum representation. See how the speech that is we are going to be speaking to the other person. So if you interpret the same thing like a time domain, and how that you are converting into the frequency domain with the help of any frequency transformation. Either you can use the discrete Fourier transform or the fast Fourier transform. Okay, so you can comfortably employ any kind of the Fourier transform in order to convert from time domain into the frequency domain. So wherein we are in focus of spectrum representation that can be focused. So coming to the measurements, average zero crossing rate will be there. Energy is also one of the measurement how we are going to be achieving for a speech signal, and the autocorrelation function. And it is very simple to implement, and which provides a useful basis for the estimating important features of the speech signal. So these are the two important things that we are going to be identifying or classifying, whether it is voice or the unvoiced classification that can be done, and the pitch estimation is also can be done with the help of the time domain measurements. So this is a random some speech in the time domain representation. So this kind of the speech you can easily identify, and here the speech will be there, and here there is no speech, and from here there is a speech, there is no speech, like this. So when you put into the time domain format, this is kind of a waveform that we are going to be looking. And if you want to convert this time domain representation into the frequency domain with the help of any transformation, then we will be able to see the spectrogram of the corresponding speech signal that we are seeing in the slide. Okay, so let us see that spectrogram. Right, so the same speech signal, how we are going to be able to see the spectrogram after converting time domain into the frequency domain. So this way, this is the shaded portion, you can easily identify there is a speech, and this is the unshaded portion, there is no speech at all. And here also the same thing. So in this region there is a speech can be possible, and in this region the speech can be possible, and here some of the background noise is also going to be accompanied. You can clearly visible from this spectrogram analysis. Okay, so this is the way how we are converting from the time domain into the frequency domain with the help of the Fourier transform. Alright, now let us see the short time behavior of a speech. So the complete speech signal, you are speaking some of the words in a time frame, and how we are calculating the energy representation. Okay, so to calculate the energy representation, I am taking only some part of the speech. Okay, that's the short time behavior of the speech they are going to be seen. So assumption is that the properties of the speech signal will change slowly with the time. So coming to the analysis frames, short segment of the speech signal and overlap one another usually. Okay, so this short segment of the speech signal that we are going to be considering. So analyzing each frame may produce either a single number or a set of number. The single number nothing but the energy that we are going to be calculating, and set of numbers nothing but the vocal tract parameter, the way how we are pronouncing any kind of word. Okay, so the vocal tract vibrating, so the speech will be produces. So which is a set of numbers, and this will produce a new time dependent sequence. So this is a mathematical representation where Q of n equal to summation transformation, that is a linear or the nonlinear transformation of the speech signal into W of n minus 1. Some windowing technique we are going to be using. So this speech signal after transforming, that will be multiplied with the window parameter. So where n is the frame index, this is the speech signal, S of m or X of m, both are same in this, and the W of m, that is a window function, which is a finite of infinite. So this is a general form how it looks like when the speed signal that is coming, and that will be given to the operator. There's the linear or the nonlinear transformation, and at the output of the first block we'll be having the transformation, and that is multiplied with the window sequence, and they will be getting the speech at the output. Now coming to the energy, I clearly mentioned the complete frame is calculating as a number, is nothing but the energy, and the short time energy is nothing but we are going to be having the only some portion of the speed signal. So this way we can easily identify. So energy is nothing but summation of x square of n, just like a mean square value. And similarly for the short time energy, and we can clearly distinguish the limits how we have considered. In the energy, the complete portion we are going to be taken into consideration, but whereas in the case of the short time energy, we are taking only one part of the speech. So this is a short time energy, which is a function of n. Actually, you can easily see from the slide. In the first figure, this is the complete x of m speed signal, and when you apply any rectangular window or any kind of the window, and this is the x square of m, this is a limit that you can easily see from here, n minus n plus 1 to n. So this is a rectangular window. So this is the short time energy we can identify. Okay, we are calculating this segment. So this is the short time energy, En equal to summation of minus infinite to infinite transformation of x of m into w of n minus n. So this is the definition of the window, w of m equal to 1 when m varies from 0 to n minus 1, or which is 0 otherwise. So this is an explanation of the short time energy, how we are going to be calculating the mean square value, and at the end you will be identifying this mean square value is multiplication with the h of m. So where h of m or h of n nothing but the coefficient of a filter, so that we are going to be considering here. So this way we need to represent the block diagram of a short time energy. Thank you students. Thank you for watching this video.